that's the perfect segue, I think, to my discussion, which is an algorithm that we developed at the National Center for Atmospheric Research. I love this photograph because, to me, it summarizes why we have bad data. These are a series of anemometers that are located on a mountaintop located just outside of Juneau, Alaska. And you can't really see it here, but there's glaciers back here. You have 120-mile-an-hour winds blowing across this mountaintop. And this is about 3 feet of rime ice on these instruments. And inside of these anemometer heads is a 1,500-watt heater. And so that's how we were collecting our wind data. Let's see here. How do I advance the slide?
Change the presentation mode.
So I'd like to acknowledge my co-investigators at Kit Goodrich, Larry Corman, and again, this was originally done at the National Center for Atmospheric Research. I'm now with NREL. And what we wanted to do is we wanted to develop an algorithm that would capture the human ability to basically assess data quality with little or no knowledge about the data. So for instance, just looking at these examples of time series data, a human would sit here, or at least a hypothetical human, I guess, would sit here and look and say, gosh, the top slide, or the top figure, that looks pretty good. The second panel, gosh, there's some suspicious data in there. The third panel, there's lots of suspicious data throughout this entire thing. So for instance, the data right here, 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 and this dispersed data there. And so how is it that we can identify that data as a human with, little or no knowledge about the time series? And so we did develop this algorithm, and it did, in fact, do what we hoped it would do in terms of identifying the data that we as a human might find suspicious. So for instance, you can see the red data points are data that the algorithm has identified as suspect in each of these cases. And the point I want to make in terms of how we did this in the algorithm was, well, let me back up and say, you're looking for bad data, but you have bad data. So if you calculate a statistic using your bad data, it corrupts the statistic. So you can't necessarily use that statistic then to find your bad data. So you need to find some method by which you can, kick in the door, so to speak, and find the bad data. And we did this by going to delay space, which is simply, here we have, a toy time series problem, or a toy time series, and we have constructed essentially a scatter plot of neighbors from that time series. So for instance, you take the first 2 points in your time series, and that becomes the ordered pair over here on this side. With them, 2, 3. And then you have the next set of points here, 3, 4, and you can find them over labeled on that plot right here. Okay. And so you can start to see that when you have 2 points here that are neighbors, and these points and these points, they all start to fall in a cluster right here. And then likewise, these transitions to this dropout region then fall off the axis, and then these 2 transitions here fall right there. So now we have these scatter plots over here, which is the delay representation of the time series. And you can see we've identified clusters in that delay space. But we've also identified clusters in the time domain. And it's this combination of looking at both the delay space and then the time domain that we're able to start building these types of quality indicators, quality flags. So now an extension to this work then might be to, it's conceivable that you could build a large class of just failures, where you just take simulated data and you can assign, say for instance, you start with your sinusoid and you introduce this blast of bad data through the middle of it. And you look at the delay space portion of that in the lower figure. And the color there is the density, so we're doing density clustering. And you could conceivably build a large number of these types of failures and use these then to train, like, say, a support vector machine using these types of techniques, or using these flags. And I'd like to draw attention to this reference of Mon Perkins, because they did do time series outlier detection using a support vector machine back in 2003. But they didn't use the same sort of clustering techniques in both the time domain and delay space that we were employing. So I think there's the real possibility for building a very skilled general quality control algorithm using the clustering techniques in delay space and in the time domain, and then using machine learning algorithms on top of that, which I find that would be very nice to have such a thing, because I've spent way too much of my career dealing with crappy data. And that's all I have.